Hey everyone, so we're going to continue on with our discussion of this unit of projectile motion, where we're going to start focusing on probably the more basic foundation of projectiles, which is vertical projectile. Now, one thing that I want to note is that this topic tends to be very tricky for people, more so than the linear motion, mainly because there's so much information that you kind of have to remember. For the most part, it's things that are hidden within the words of the question. So, one of the things that you're going to constantly hear me mention is that there's hidden pieces of information. We didn't really have that in the previous topic. If they give you a number, that's it. The most hidden a piece of information was when they said the phrase coming to rest or starting from rest. But here, there's going to be a lot more hidden pieces to talk about. So, as we all know, the whole idea about gravity was discovered by Sir Isaac Newton. Of course, it was always there, but he kind of came up with the name of it and the concept behind it. Basically, he was relaxing in the garden, apple dropped on his head. All of a sudden, he thought, huh, I wonder why that happened. There's other counts that he was actually looking at the moon and trying to think about why the moon was staying up there, why it moved across the sky, why it doesn't fall down, things like that. And that's where he kind of came up with this idea of gravity. So, he basically started asking himself all these things. Does this idea of gravity affect all objects? Does it affect some objects more than others? What's causing this gravity? Is there a limit to this effect? Uh, you probably heard this before. Gravity is just a theory. Um, it Now technically it actually is a theory and a law. There's a theory of gravity, which is what's causing it, and then the law of gravity is one of the things that we'll talk about later on. Very quick side note for those who didn't know: the main difference between a theory and a law is not that one is tested more than the other, or one is more concrete or accurate than the other. The difference between a theory and a law is that a theory is an explanation. It still can be proved and tested and experimented on, but a theory is an explanation of why something happens, while a law is a statement of that something happens. So you'll see examples of this in the next topic when we start talking about Newton's laws of motion. So, as I said, he came up with this idea of gravity, that gravity pulls all objects down to Earth. In fact, it's what kind of attracts all masses. It keeps us on Earth. It keeps the moon connected to the Earth. Keeps the tides on the Earth moving around. It also keeps us around the sun and all these other things. So, pretty much, gravity is what binds everything together. Now, the next thing he wanted to know was, is this something that affects all objects differently? Are certain objects more affected by gravity than others? So he wants to see, does mass matter? Now, in the real case, as you probably know, if you drop a textbook and a piece of paper, one is going to land first. The textbook's going to land first. In fact, it happens all the time. There are times where you drop one object and it'll hit the ground before another object goes. That's because there's other things involved. Stuff like the shape of an object will affect how it falls. Things like feathers are less aerodynamic, so they'll end up lilting and falling very slowly compared to a penny. So it does in the real case uh, affect differently, but if you took objects that were identical for the most part, different masses, but for the most part very spherical and similar in size, then the effects of the air wouldn't really occur as much, and we'd end up finding that they actually do land at about the same time. Uh, you probably heard of Galileo doing this off the Leaning Tower of Pisa by dropping two balls of roughly equal sizes but different masses. So he came out with this idea that mass does not matter when it comes to when objects hit the ground, the acceleration caused by gravity. So all objects will fall at the same rate. Uh, through tests and trials and things, we found that the acceleration due to gravity is 9.8 meters per second squared. Now, because this is a constant term, something that is regularly used, we tend to give the this number the symbol of little g. But don't forget, this is an acceleration. So this can be plugged into any acceleration equation that we have. Just want to throw that out there. It's not limited just to little g equations, as you'll see later on. So this is on the reference table. It's on the front page, in fact. If you look on the back page, it's called the acceleration due to gravity. It is given a second name called the gravitational field strength. You're not really going to see that a lot. You're mainly going to see it called by the acceleration due to gravity. But yeah, just keep that in mind. This is a very important number. You want to memorize it. But if you want to make your life easy, you could just round this number very easily to 10 meters per second squared. So I kind of recommend using this number. Just realize that if you do any calculations using 10 meters per second squared, the number that you get as an answer is going to be slightly off. Not drastically off, not enough where you couldn't tell which one the correct answer is, but enough where you won't see that exact answer. So just keep that in mind. Alright, so this is kind of one of the things I said. This is still an acceleration. So any equation that has a, we can use 9.8 in for it. And another warning that I need to say is that this is only an acceleration for falling objects in the air. If you have an object rolling on a table, it is not accelerating at 9.8. If you have an object in the river, it is not accelerating at 9.8. There are very many times where people, after doing this topic, when they revisit the linear motion questions, when they come up across a question that doesn't have acceleration, because of this unit, they'll think, oh, I can just use 9.8. That's probably my acceleration. But remember, the 9.8 only is true for objects that are falling in air, that are in the air moving. And also, don't forget that gravity always acts downward. So, regardless of how an object is moving, whether it's moving up, down, left, right, the acceleration caused by gravity is always going down. If you ever forget the direction of gravity, just pick up your pen, drop it, and see where it goes. And like I said, remember that there is a difference between velocity and acceleration. This is where this difference is going to start becoming more noticeable, and people are going to start confusing the two. So you want to make sure that you keep them separate. So, as you probably know, Newton came up with it when he started doing studies on gravity. He realized that mass is what really affects gravity. We're going to show an equation of where it comes from, but for the most part, the more mass an object has, the more gravity it's going to have. That's why Jupiter tends to have more gravity than Earth does, or the Sun has more gravity than us, is because it's more massive. So if you didn't know who this man is called Felix Baumgartner. He ended up breaking the record for the highest free fall ever. Also, a few other records he broke are things like the fastest speed, breaking the sound barrier without any sort of device or automobile or rocket. So we're going to start off in our projectile motion topic talking about the very easiest topic of free falls. So this is the very basic, fundamental type of projectile. Now, a lot of times you'll know that you're dealing with free fall based off of the wording. An object is dropped from a height. An object falls freely. Clearly, falls freely means it's a free fall problem. The reason why these are free fall problems is mainly because there's two pieces of information that you aren't going to be explicitly told, but you automatically know in the problem. The first is that the initial velocity is zero. When it says that the object is dropped, that means it's starting from rest. It's not thrown down, It's not tossed, it's not lobbed or anything like that. It's dropped, meaning you're letting it go and it's starting from nothing. The other is that the acceleration is 9.8. So, and that's because it's dropped on Earth unless said otherwise. So with these two pieces of information, we can answer a lot of these problems. The reason I point this out is because when you first look at a freefall problem, you're going to notice that you're probably only going to be given one piece of information: a height, a time, a final speed. And at first, you might not think that you have enough pieces to actually answer the problem, to figure out what equation to use. But the whole idea is that these are two more pieces that you automatically know based off the wording. So one thing that you can do is start writing your given piece of information, the ones that pop out, and then think to yourself, well, if I'm using my motion equations, what other pieces would I need in order to find what they're looking for? And then ask yourself, maybe do I know what the initial velocity is? Maybe I know what the acceleration is. Is it possible? And that might remind you that you do know these two numbers. Now, of course, it is always possible that you might do a problem where the initial velocity isn't zero. Again, though, it will usually tell you what that speed is, and it will say that it's thrown down or something of that matter. But the whole thing is that it doesn't really change anything else with the problem. All it is that you just add in a new initial velocity. All right, so here's the first question. Pause the video, work on itself, and we'll go over in a second. All right, so the first question, it wants to know how much time it takes for the penny to hit the ground. Again, as you can see, there's really only one number that they tell me. The distance is 443 meters. But again, the other pieces that I know are the initial velocity and the acceleration. Now, one other thing that I probably should have mentioned is this. They say, how much time does it take for the penny to hit the ground? A lot of people are going to assume that the final velocity will also be zero because when it hits the ground, it stops moving. However, whenever we deal with these freefall problems, the object never hits the ground. That is very important. Once it hits the ground, that's a different type of problem. So when we're doing these problems, it's the moment just before it's about to hit the ground. So it's still technically moving, but it hasn't hit the ground yet. The final velocity will not be zero just because it hits the ground. It's actually going to be something before it hits. All right, so they're looking for the time. So what I want to do is based off of what I have, d v I a t, I'm going to use the magic d equation. D equals VIT plus 1 half AT squared. I'm going to plug in my numbers, 443. Just to make my life easy, I'm going to immediately cancel this entire section out because it's zero. You're going to see this happen a lot. I know I wrote 9.8, but I'm actually going to round it to 10 right now. T squared. So solving all this, we end up getting that the time is going to be 9.4 seconds. All right. And then part B, what's the final velocity? So I have all these pieces. Normally you'd have to rewrite them, but I don't have the time. So what I'm going to do is I can actually pick any equation that's final velocity. I'm going to go with the simpler one, Vf equals Vi plus At. I know my Vi is 0. I know my acceleration is about 10, and I know my time is about 9.4. So I get a final velocity of about 94 meters per second. Now, very quickly, if you instead used the 9.8 number, you'll realize that your answers aren't that much off from mine. The time would have been 9.5 seconds, and the final velocity would have been 95 seconds. Again, there really is not that much of a difference. Oh, sorry, not 95. Um, 93. So not that much off. Point 0.1 here, 1 over here. Very small difference, which is why I said you can easily use 10 just to make the calculations easier. All right, here's the next question. Pause video working itself, and we'll go over it in a second. All right, so once again, they give us a time, but because I need more pieces, when I read the question, it's dropped, so it's initial velocity 0, and because it's on Earth, I know my acceleration is going to be about 10, and they want the height. All right, so once again, I'm going to use, oh, look at this, the magic D equation. I said before that this is your main equation, and this is why. In this unit, you are going to be using it a lot. In fact, it's actually the reason we call it the magic D, is because this unit in particular uses it so much that if you're stuck, just ask yourself, can I use the magic D? And try to use it, and chances are you'll probably end up getting it right. All right, and I believe the distance should be about 45. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so here, now we're on a different planet. So our acceleration is not going to be 9.8. In fact, that's what we're looking for. So we're looking for the acceleration. It starts from rest, so we know our initial velocity is 0 again. Our final velocity is going to be 12. And our distance is 14.4. The only piece of information they didn't mention is time, so I'm going to use my timeless equation. It is the only motion equation without time. Vf squared equals vi squared plus 2ad. Plugging the numbers in, we get 12 squared equals 0 plus 2a times 14.4. Doing all of this, dividing over, we end up getting the acceleration is equal to 5 meters per second squared. All right. Here's the next question. Pause the video, work itself. I'll go over in a second. All right. So they want to know the ratio of the rock's speed to the stone speed. Well, first off, the only difference between these two objects is their mass. They start at the same height, they fall for the same amount of time, they're accepted by the same acceleration due to gravity, they start at the same initial velocity. So everything about their motions are the same. The only difference is their mass. But I said before that mass doesn't matter, especially in an ideal case like we always deal with. So their speeds should be the same. So it should be a 1-to-1 ratio. All right, here's the next question. Pause the video, work itself. We'll go over in a second. All right, so now in this question, it is no longer being dropped from a plane. He's actually jumping from a plane. So they tell us that the initial velocity is 20. They tell us that the final velocity is going to be 120. We know the acceleration is 10 because, again, it's on Earth. And they're looking for time. So use my acceleration equation. Vf equals vi plus at. 120 equals 20 plus 10 times t. And we're going to end up getting 10 seconds for the time. Part B, they want to know the distance that he falls during this time. So I'm actually going to use the magic D. D equals VIT plus 1/2 AT squared. The initial velocity is 20 times 10 plus 1/2 10 times 10 squared. So this is going to be 200 plus 500. which is 700 meters. Now, one thing I probably should mention, yeah, one thing I should probably mention is that you may notice that I haven't been putting any sign on this acceleration, even though the acceleration is downwards. I don't have to mention it right now. See, I said before that the whole idea about negatives being down and positive being up, I said that was convention, but you don't have to do it as long as everything is consistent. I did mention that point that it only matters when you have different directions. Everything about these motions are going down. So because of that, I don't have to worry about signs because technically every number would be negative. Um, yeah, like I said, in this class, we're going to assume that these objects are free falling in ideal cases without air friction. Air friction is what actually keeps objects falling at different rates. So we're never going to really talk about air friction, uh, but it is important to know kind of what effect it will have on an object. You won't have to do any calculation, you just need to know conceptually what's going to happen. So the whole idea is that air friction will actually cause objects to move slower. They're going to decelerate more as they go in. That means that when you throw an object, objects won't go up as high in the air as they would ideally. They won't go as far, and they won't drop as fast. So the whole idea is that everything's less when you deal with air friction. Now, another thing about air friction is that at a certain point when objects are falling, there's going to be a moment where actually it's not just a moment, but a period of time where the air friction that's decelerating them upwards actually counterbalances the acceleration of gravity pulling them down. So those two accelerations cancel out and the object will start to move at a constant speed. This is what's called terminal speed or terminal velocity. Basically, it's the fastest an object can move based off of the balancing of air friction. So one of the comments I'm sure you've probably heard is that you drop a penny from the Empire State Building, hit someone on the head, and it's going to go straight through. It won't actually do that. In fact, the terminal velocity of a penny is about 30 meters per second or 65 miles per hour. It'll hurt a lot. It's about the same speed that if you just threw it into someone's face point blank, it would hurt them a lot, maybe leave a mark or maybe break some skin, but it won't kill anyone. The Empire State Building is just high enough for a human to reach terminal velocity during their free fall, which is going to be about 53 meters per second. So anything higher than the Empire State Building, and objects will actually hit the ground at the same speed. Very interesting. And then, as I said before, Felix Baumgartner was actually the first and only person to ever break the sound barrier during a free fall. And just for reference, the sound barrier is 373 meters per second or 834 miles per hour. So very interesting. I'll show the video for those in class and I'll talk a little bit about it because it is kind of interesting. That's pretty much it. So we'll have you do some practice questions with more free fall stuff before we go on to the next part with vertical projectiles. If you have any questions, let me know. Otherwise, good luck and have a great day.